We're going to work some problems here to review for the Chapter 4 test. So for the first one, we have f of x equals x squared minus 1 to the 2/3 power. We're going to try to find the intervals where f is increasing and decreasing, find any relative extrema, find what the intervals where f is concave up and concave down, find any inflection points, and then use all of that information to draw a graph. So we'll start with the first derivative stuff. So we're going to take the derivative, and we've got a chain rule derivative, 2/3 times x squared minus 1 to the negative 1/3 power, and then times that 2x. So a little cleanup, that's going to be 4/3 times x. Let me write it this way. I think I'll write it as 4 times x over 3 times, and then x squared minus 1 to the 1/3 power in the denominator. So there's our derivative. We're going to set it equal to 0. So we want places where the derivative is equal to 0 or undefined, and these we will call critical points. So that just amounts to setting the numerator to 0 and solving, and setting the denominator to 0 and solving. So the numerator will be 0 at 0, and the denominator will be 0 at 1 and negative 1. So we'll do a number line here, and I'm going to put in 0 and negative 1 and positive 1 and label that as f prime. To the left of negative 1, if I plug in negative 2, we'll get a negative numerator. And when we plug in a negative 2 squared is 4 minus 1 will be positive. So the denominator is going to be positive. And so a negative divided by a positive is negative. If I put something in between negative 1 and 0, like say negative 1/2, the numerator is again going to be negative. But now because negative 1/2 squared is 1/2, or 1/4 rather, minus 1 will be a negative. Cube root of a negative is negative, so we'll have a negative on the bottom as well, making that a positive. With a positive 1/2, now the numerator becomes positive, but the denominator remains negative, making the quotient negative. And if I plug in something like, say, 2, then everything's positive, numerator and denominator, and so we'll get a positive. So the answer to part A, f is going to be increasing on the closed interval from, closed interval, so from negative 1 to 0, and also from 1 to infinity, and f will be decreasing on the interval from negative infinity to negative 1, including the negative 1, and from 0 to 1, including both endpoints. So then I guess we might as well find out where we have these, it didn't ask for it, but we do need extremas, so let's get that. So we see that at negative 1, that the derivative goes from negative to positive, so that's going to be a relative minimum, and we plug this back into the original. And when you plug negative 1 into the original, that's going to become 0. And at 0, we're going to have a relative maximum because our derivative goes from positive to negative. So at 0, we're going to get 0 squared is 0, minus 1 is negative 1, cube root of, I'm sorry, I put in the wrong one, but it still worked out the same. We got to put it into the original. So plugging in negative 1 still gave us 0. Plugging in 0 will be a negative 1. The cube root of negative 1 is negative 1. Square that is positive 1. So that's going to be at positive 1, 0, 1. And then we're going to get another relative minimum when we plug in 1, and that's also going to be at 0. So we have two relative minimums at negative 1, 0, and 1, 0, and a relative maximum at 0, 1. So let's figure out what we can get from the second derivative. So we're going to take f double prime of x. Oh boy. So we're going to use our quotient rule. So we have the denominator, 3 times x squared minus 1 to the 1/3 power, times the derivative of the numerator, which is just 4, minus the numerator, which is a minus 4x, times the derivative of the denominator. So we're going to take 1/3 times the 3, That's going to cancel that. We'll get x squared minus 1 to the negative 2/3 power, and then times the derivative of the inside, which is 2x. All of that is going to be over the denominator squared. So we'll get a 9 and an x squared minus 1, and when you square 1/3, we'll get 2/3 power. So in the numerator, we're going to try to do some factoring here. So let's see, it looks like we have a common factor of 4. I think we'll pull that out. And we're going to factor out the smaller of the powers of x squared minus 1. And x squared minus 1 to the negative 2/3 is smaller. And I think that's going to be about it. So that's going to leave behind. We took the 4 out, but there's still the 3. And we took out x squared minus 1 to the negative 2/3. So when you factor something out, you divide by that. So if we divide the x squared minus 1 to the 1/3 by the x squared minus 1 to the negative 2/3, we'll subtract exponents. That's going to end up being x squared minus 1 to the first. We have a minus. We took out the 4. We took out the whole x squared minus 1 to the negative 2/3. But we're still going to have, it looks like a 2x squared. And that's going to be all over our 9 times x squared minus 1 to the 2/3. So the 4 we're going to leave outside there. That x squared minus 1 to the negative 2/3 will move into the denominator. That will add to that power of 2/3 down there, making it x squared minus 1 to the 4/3. Inside the bracket, if we distribute, we're going to get 3x squared minus 3 minus 2x squared. So finally, we're getting to 4 times, and I think that will be x squared minus 3. And we've got the 9 and the x squared minus 1 to the 4/3. So again, this is our second derivative. We're looking now for pips. These are potential inflection points, and they are going to come from where the second derivative is 0 or undefined. So we will set x squared minus 3 equal to 0, getting x squared equal to 3, getting x to be a positive or a negative square root of 3. So there's 2 pips, and then like we saw before, where the denominator is 0, which is going to be plus or minus 1. So let's see what we're getting from the second derivative. Here we are with f double prime, and there's going to be 0, and there's going to be 1 and negative 1. I'm kind of trying to line them up with what we got for f prime. And see, square root of 3 is going to be a little bit less than 2, so I'm going to say maybe not quite that far. So maybe right in there is going to be square root of 3, and I'm going to extend this a little bit. Somewhere right in there is a negative square root of 3. So if we put something to the far left, like say negative 2, negative 2 squared in the numerator is 4 minus 3 will make the numerator positive. And in the denominator, it doesn't matter what we get because this 4th power down there, our denominator is always going to be positive. So positive over positive is going to make that be a positive in here. Something in between negative 1 and negative 3, like say negative 1.5, say negative 3/2. Squared is, maybe even like a negative 1, let's go even smaller than that, negative 1.1. Well, we're smaller than square root of 3, so when we square it, it's going to be less than 3. So when we subtract 3 from it, this will now be negative. Denominator is always positive, so that's going to be negative. In between 0 and 1, then what if we get squared will still be less than 3, so that's going to remain negative in the numerator, remain positive in the denominator, that's going to be negative. And likewise with a positive value, say 1/10 or something, squared is going to be less than the minus 3, so the difference will be a negative over the positive is still negative. And something like just a little bit bigger than 1, but not yet to square root of 3, so when we square it, it'll be less than 3, still negative in the numerator, positive in the denominator, and then finally when we're bigger than square root of 3, we're going to get a positive in the numerator, making this a positive. So to answer our part C, where's this concave up, concave down? We're going to say that that F is concave down. Now, let's see, it's not going to be defined at -1 and 1, so we're going to need to say it's going to be concave down on the open interval from -√3 to -1, also on the open interval from -1 to, now 0 is no problem because it's defined there, so all the way to +1, and then again from 1 to √3. F will be concave up from -∞ to -√3, and also from √3 to +∞. So let's see, we're going to have inflection points. So our part D, our POIs, points of inflection, are going to be where it changes sign. So that's going to be, whoa, come back here. It's my left-handedness getting in the way. So it's going to be at -√3, comma, and -√3 squared is 3, minus 1 is 2, squared is 4, so it's going to be the cube root of 4. Not the greatest number in the world, but we can live with it. And also at +√3, which will also be a cube root of 4. Okay, see if we can put it all together in a graph. Let's see, I think most of the stuff here is happening above the x-axis. So we know that we have a relative minimum at -1, 0, and a relative maximum at +1, 0, or another relative minimum rather, at +1, 0, a relative maximum at 0, 1, and we have inflection points at -√3, cube root of 4, and +√3, cube root of 4. So let's see, √3 is in between 1 and 2, and the cube root of 4 is bigger than the cube root of 1, but smaller than the cube root of 8, so it's going to be in between 1 and 2. So we're approximating that here, and I think we're going to get these points right there where it's going to change concavity. So let's see. To the left of -√3, we are decreasing and concave up. So decreasing and concave up. In between -√3 and -1, we are decreasing and concave down. I didn't leave myself very much room there. Then we're going to increase to 0, but still stay concave down. And then we're going to decrease to 1, but still stay concave down. And then we're going to increase to √3 and still stay concave down. And then we're going to increase but go to concave up. You know, it's not the greatest picture in the world, but something like that. All right, let's look at the next screen. So let's see if we can find the relative extrema for this piecewise function. So we're looking for a relative extrema on both branches first, and then we want to consider the point where they come together. Now on the left branch, 5 minus 2x is just a line, so it's not going to have any relative extrema, so it's not going to contribute anything. Now the 4x minus x squared is a parabola that opens down, so its derivative is going to be 4 minus 2x. If we set that equal to 0, we'll get 4 equals 2x, so x equals 2. That is in our domain, so we do need to consider whether that's going to be a relative min or a relative max. So looking at the number line just around 2, and I got to stay in between, I got to watch where I'm going, how far left we go there. So if I plug in something like maybe just 1.5, then 2 times 3/2 is going to be 3, so we're still going to be positive. And if I plug in something bigger than 2, like 3, then we're going to go to negative. So we are, in fact, going to get a relative maximum at 2, and that gets plugged into our bottom branch there, the 4x minus x squared. So 4 times 2 is 8, minus 2 squared is 4, is going to be 4. That's a relative maximum. Now let's see what's going on with this, this point where they come together. So when we plug in 1 to the top branch, 5 minus 2 is 3. When we plug in 1 to the bottom branch, 4 minus 1 is also 3. So it is going to be continuous. So we're going to come down with our slope, our line that has negative slope, and then we're going to pick up part of this parabola here. So it looks like we have a potential corner point there. It's going to be continuous, but we need to look at the left-hand derivative compared to the right-hand derivative. So at x equals 1. So the left-hand derivative is the derivative here. So the left-hand derivative is going to be a negative 2 all the time, no matter what you plug in for x. The right-hand derivative is going to be, as we said, 4 minus 2x. And so at x equals 1, then that's going to be 4 minus 2 times 1 is 2, is going to be a positive 2. So since the left-hand derivative is different than the right-hand derivative, that's going to be a corner point, but that makes it a critical point because the derivative is undefined there. And we can see that the derivative to the left, so if we're doing our number line here, and here is 1, we can see that the derivative to the left is negative, and the derivative to the right is positive. So that means we're going to have a relative minimum at 1, and the parts, and we said that it's going to be equal to 3 at x equals 1. So we have a relative minimum and a relative maximum. Crazy. Okay, now let's do the next one. Can we find the maximum? So we're looking for an absolute maximum, capital M, and the minimum, little m, for f of x equals 4x plus 1 over x on the interval 1 to 4. So to find absolute max and min, we're thinking that's going to be a candidate test. So for the candidate test, we need to find the derivative, set it equal to 0, find any place where our function is 0 or undefined, that is, find the critical points on that interval. So the derivative of 4x is 4. The derivative of x to the negative 1 is a negative x to the negative 2. So we can think of that as 4 minus 1 over x squared. We're going to set that equal to 0. We notice that x equals 0 would be a critical point, but 0 is not on our interval, so it's not one that we're going to be interested in. If we set this equal to 0, we're going to get 4 is equal to 1 over x squared. So that means that 4x squared is equal to 1. So x squared is 1/4. So x is going to be positive and negative 1/2. Now again, negative 1/2, neither one of them is on our interval. So neither positive nor negative 1/2 is on our interval. Guess we got off the hook on this one. So all we need to check now is f of 1 and f of 4. So plugging in 1 to the original function, that's that's going to be 4 plus 1 is 5. And plugging in 4 is going to be 16 plus 1/4 is 16 and 1/4. So this is our minimum, and this is our maximum, and we've justified it because we used the candidate test. All right, next panel. Here we are going to see that we have this crazy function, f of x equals 2 over x squared plus 1, which is graphed for us in yellow. And we are going to find the dimensions of a rectangle of largest area inscribed between the curve and the x-axis. And a representative rectangle is shown in the green there. So we know that the area of a rectangle is length times width. Now we want to get this to be a function of x, so if we look at a shared point on the curve and the rectangle, we can see that because this distance here is x, its x-coordinate is x, and because it is on that yellow curve, its y-coordinate has to satisfy 2 over x squared plus 1. Now we can see that the base, or I'm going to call that the length of our rectangle, will be 2 times that x from the symmetry. And we can see that the height, or I'm going to call it the width of that rectangle, is going to be that vertical distance, which is going to be the y-coordinate of that point, which is going to be 2 over x squared plus 1. So our area is going to be given by 4x over x squared plus 1. Now we are looking for the largest area, so we're looking for an absolute maximum. But we can see that it doesn't appear that we have any reason to limit our domain. So the hard part on this one is it appears that the domain is all real numbers, which is going to make it a little more challenging to come up with an absolute maximum. We'll see if we're up to that challenge. So we want to find the critical points first, so we're going to take the derivative. So we're going to get the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. We want to set that equal to 0, and we want to know what makes the numerator 0 or the denominator. Now the denominator we can see is never going to be 0 because anything squared is positive, and a positive plus a positive 1 will never be 0. So we direct our attention just to the numerator, and so if we distribute, we're going to get 4x squared plus 4 minus 8x squared we want to be equal to 0. So the 4x squared minus 8x squared is a negative 4x squared, and if we add the 4x squared to the other side, divide by 4, and take the square roots, it looks like we can get a positive or a negative 1. So what we need to do now is try to make an argument about which of these is going to be the maximum. Now, if this is our area right here that we're trying to maximize, so we have this area is 4x over x squared plus 1. So if we evaluate this at negative 1, we can see we're going to get 4 times negative 1 is negative 4. Negative 4 over 2 is negative 2. That doesn't even seem like a reasonable area. And area of positive 1 is going to be 4 over 2 is 2. And we can't plug in the endpoints. So instead of that, what we're going to do is consider the limit as x goes to positive infinity of our area, and the limit as x goes to negative infinity of our area. If those turn out to be smaller than our 2, then we can be confident that that is in fact our largest area. And if it isn't, then we're in trouble because we're not going to have probably a biggest one because it's going to be approaching that. It won't actually be equal to it. So as x gets really, really big, you can see that the denominator is going to outpace that. So we're going to get 0, and in a similar fashion, we're going to get 0 there. So our absolute maximum area is going to be the 2, and the x value was 1 that led to that maximum value. That is one of our dimensions because remember our rectangle was 2x rather. So one dimension is going to be 2. That's going to be our base or length. And then when we plug in 1 to our y value, that's going to be the height. And so the height will be 2, or length is 2, and width is 2. Very good. Now we'll go on to the next screen. So here we have f of x equals x cubed minus 7x plus 6. Can we verify the mean value theorem applies to f on the interval from 1 to 3 and find the value of c that satisfies the conclusion of the mean value theorem? So trying to understand our the conditions for the mean value theorem. So we need f is continuous. All we need it is on the open interval we do need it continuous on the closed interval from 1 to 3, and f is differentiable on the open interval. And that is easy to meet here because f is a polynomial. And so it is continuous and differentiable everywhere. And we can see then also that we have a closed interval. So we'll say 1, 3, because of the brackets, is a closed interval. And so we have satisfied the conditions that we need. So now what we need is f of b minus f of a over b minus a. So for us, that's going to be f of 3 minus f of 1 all over 3 minus 1. So f of 3 is going to be 3 cubed minus 7 times 3 plus 6. That's 27 minus 21 plus 6. So I think that's going to be 12. F of 1 is going to be 1 minus 7 plus 6, which is 0. So we get 12 minus 0 over 2, so that's 6. So our average rate of change, or the slope of that secant line from from x equals 1 to x equals 3 is 6. That must equal our function, or our derivative rather, so we better find f prime of x. F prime is 3x squared minus 7. So if we set that equal to our derivative, 3x squared minus 7 equal to 6, then hopefully we can solve this. So if we add the 7 to the other side and divide by 3, we can take the square root of that and get plus or minus square root of 13 over 3. Now the negative square root of 13 over 3 is not going to be between 1 and 3, but the square root of 13 thirds, because 12 thirds would be 4, and square root of 4 is 2, or a little bit bigger than 2, but that is going to be in our interval, so that is our value of c that is guaranteed by the mean value theorem. Very good.